Electricity is not magic. It's just moving charges. Let me explain simply. Electricity is the flow of electric charge, usually electrons, through a conductor like copper wire. Think of electrons like tiny particles moving from one atom to another. When they move in a directed path, we call it electric current. This flow happens because of voltage, which is like electrical pressure pushing electrons forward. Without voltage, electrons don't move. And without current, no device can run, because current is what carries energy. Every light, fan, charger, motor, and computer works because electrons flow through circuits in a controlled way. Understanding this simple idea is the foundation for all electrical engineering. Follow the series to build your electrical basics step by step. These three terms control everything in electricity. Voltage is electrical pressure. Current is the flow of electrons. Resistance is the opposition to that flow. The relationship between them is given by Ohm's law. Voltage is equal to current into resistance. If voltage increases, current increases. If resistance increases, current decreases. This simple law is used in every electrical design: bulbs, chargers, motors, circuits, and even your phone's battery management. Engineers calculate wire size, fuse rating, and device power using this exact formula. Mastering Ohm's law means mastering electrical basics. Your phone uses DC, your home uses AC. Why the difference? DC, or direct current, flows in one direction, used in batteries, solar panels, and electronics. AC, or alternating current, changes direction 50-60 times per second, used for homes and industries. AC is easy to step up or down using transformers, making it ideal for long-distance transmission. DC is stable and perfect for small electronics and storage. Modern devices combine both using converters and adapters. Together, AC and DC power the entire world, from high-voltage transmission lines to tiny microchips. Ever wondered what 100 watts actually means? Electrical power is the rate of energy use. The formula is simple. Power is equal to voltage into current. A 100-watt bulb uses 100 joules of energy every second. Energy consumption is measured in kilowatt-hours. If a 100-watt device runs for 10 hours, it consumes 1 kilowatt-hour. Your electricity bill is based on these kilowatt-hour units. Watch the next episode to understand circuits. Understanding power helps you choose efficient appliances and reduce costs. Why does one faulty bulb break all lights in a series circuit? In series circuits, current flows through each component one after another. If one bulb fails, the entire circuit breaks. Voltage divides across components, but current stays the same. In parallel circuits, each component gets its own path. If one bulb fails, others stay on. Voltage remains the same across branches, but current divides. Homes use parallel circuits, so devices work independently. Understanding this is key in wiring, electronics, and solar design. How can a small device step 11,000 volts down to 230 volts? A transformer changes AC voltage levels using magnetic induction. It has two coils, primary and secondary. AC in the primary coil creates a changing magnetic field. This induces voltage in the secondary coil. More turns, higher voltage, fewer turns, lower voltage. Transformers are everywhere: chargers, power stations, appliances. They enable safe power distribution across cities and homes. Your breaker trips to save your home from a fire. Here's how. A circuit breaker protects wiring from excessive current. It has two mechanisms: thermal trip, for long-term overload, magnetic trip, for sudden short circuits. When a fault occurs, the breaker opens instantly, breaking the circuit. Inside, arc chutes extinguish the electrical arc safely. Without breakers, wires could overheat and catch fire. This is one of the most important safety devices in any electrical system. Electric motors are everywhere, from fans to trains. A motor converts electrical energy into mechanical motion. When current flows through a coil in a magnetic field, a force is produced. This is the Lorentz force. This force creates rotation. AC motors use alternating current to rotate smoothly. DC motors use commutators to change direction. Motors power fans, EVs, pumps, compressors, robots, almost everything that moves. Understanding motor basics is essential for any electrical engineer. Power factor tells us how efficiently electrical power is being used. When you use AC electricity, not all the power is converted into useful work. Some power bounces back and forth between the load and the source due to inductive or capacitive effects. This creates what we call reactive power. A power factor of 1 means perfect efficiency, but in motors, fans, pumps, and refrigerators, power factor is usually lower because of their inductive nature. Low power factor increases current flow in the system, causing voltage drops, overheating, and energy loss in the wires. Industries are often penalized if their power factor is too low, so they install capacitor banks to improve it. Better power factor means lower electricity bills, less stress on transformers, and more stable voltage. This concept plays a major role in electrical engineering and power distribution. Three-phase power is the backbone of modern electrical systems. Instead of a single AC waveform, it uses 3 waveforms spaced 120 degrees apart. This creates continuous, balanced power flow with no pulsations. Three-phase motors run smoother, more efficiently, and with higher torque compared to single-phase motors. Power transmission becomes more efficient because currents are balanced across phases. It allows thinner wires, reduced losses, and better voltage stability. Most industries, factories, pumps, and large buildings rely on 3-phase systems for running heavy machinery. Even your home receives a single phase that comes from a 3-phase distribution system. 3-phase power is one of the biggest reasons modern electricity grids can handle massive loads reliably. Earthing, also called grounding, protects people and equipment from electrical faults. If a live wire accidentally touches a metal body of an appliance, the metal becomes energized. Without earthing, touching that appliance can cause a serious electric shock. But with proper earthing, fault current immediately flows into the ground through a low-resistance path. This causes the circuit breaker or fuse to trip instantly. Earthing also protects sensitive electronics from voltage surges caused by lightning or system faults. There are different types of earthing systems like TT, TNS, and TNCS used worldwide. Even your home has an earthing rod buried underground to ensure safety. Good earthing saves lives, prevents fire hazards, and keeps electrical systems stable. Voltage drop happens whenever current flows through a long cable. Every wire has resistance, and as current travels through it, some energy is lost as heat. This causes the voltage at the load end to become lower than the supply end. The longer the cable, the higher the current, or the thinner the wire, the bigger the voltage drop. That's why power engineers use thicker cables for long distances and high-load equipment. Too much voltage drop can make motors overheat, LED lights dim, and appliances underperform. Calculating voltage drop is an essential part of electrical design to ensure stable and safe operation of all connected devices.